Hello, welcome to Bedroom Builds at the From Python to Rust series, episode 1, Variables and Numbers. Last episode we looked at the syntax differences between the two languages, and we'll continue in that theme now with declaring variables and looking how numbers are treated. Let's jump into code for variables. Here on the left again we have our Python code, on the right we have the Rust code. It looks very similar if we start comparing this. Like last time, we can see a declaration of x being 1 is fairly easy in Python, and in Rust it's very similar. You just have to use the let statement and add a semicolon for this to be valid. Below we print it in Rust here and in Python. Then we can shadow this variable or redeclare it if you want. Here being a single character, this also works in Rust perfectly fine. So even though this is in the same code block of the same function, it doesn't care. Now x is just meaning this I, the single character. Then we can declare stuff and initialize it. This works not really in Python. You would have to tell this variable is now being none at the start, for example. Then you can continue declaring other stuff. Then you might print that and then do actual initialization of something, in this case 5 times x. This works in Rust as well. In this line you can see that we just let something be a declaration, but no actual value, no type declaration, nothing. Then we keep declaring something else, like x becoming a 5, as we did in Python. Then we try to print this, and next we actually initialize something to have a value. So this is actually here. From here on out, something is initialized and usable. Then concept of mutability. Mutability means that a variable, if it is mutable, can be changed and have a different value in the course of the program. And immutable means it cannot. By default in Python, everything is mutable. Therefore, this concept doesn't really exist. So this code just works like that we can see here. Y is 0, below we go y times 2 plus x, and then we have computed this, and we can print the output. The very same code in Rust would look like this. We declare it, we do the computation, and here we do our output. Here I introduce a new interesting macro. I will explain more once we run the code. And then we would have the concept of constants, so something that cannot be changed. Again, as already said, in Python that doesn't really exist because everything is mutable, therefore also a constant. By convention, in Python, you would use all caps as a variable name. And this just means to another programmer, oh, this is supposed to be unchanged and this is a constant that we can use. In Rust, this exists. So you use the const keyword and a type definition and the value that you want to assign to this constant. And after that, this can never be changed. And that helps the compiler quite a bit because it knows, oh, this is something I can put on a fixed place on the stack and do optimized compilation with. Now let's try to run this code. Now running this code means that we have to jump to our output thing and we run Python variables and everything works. There's no problem whatsoever. We can see the one output of this print x, then we put the I, this is that one. Then we get our first line from our declaration and the initialization a bit later. So first line would be this one that shows none. And after the computation that has been done here, we get our output of 25 instead of none. Mutability is shown since x is still 5 from up here, and we do this math where this becomes still 0. We end up with 5, so we get this as an output. And the constant we never put out, so there's no output for us to see. Let's jump over to Rust. Okay, let's run our Rust code. This means compiling first, so we use the Rust compiler variables.rs, and it complains, rightfully so. First error we run into is fairly obvious, because in our declare initialize example, we are actually trying to use the only declare but never initialized value, and this is exactly what it tells us, the compiler here, use of possibly uninitialized something. Yeah, there is not much it can help us with. We just have to remove that code. And Rust helps us to not shoot ourselves in the foot by not letting us do that. Therefore, this is a straight up error and we have to correct it by deleting this line. Let's save and see what the compiler gives us now. We still have a second problem in our code. This is now about the mutability that we spoke about before. By default, in Rust, everything is immutable. So if you want to have a variable that can be changed and be mutable, you would have to tell the compiler, and this is exactly what makes the compiler amazing. If it knows how to fix it, it will actually give you hints what are the ways to make your code work. In this case, it actually has this helpline right here that says make this binding mutable. And it also explains to where it ran into the issue. So on line 17, we have tried to do the computation, and actually further down, we do it again. In 21, we do another computation that involves assigning to y, and it cannot do that because it is immutable. Now let's fix this in the code. We would go to line 16 and add the mutable keyword as the compiler wanted us to do. Let's run the compiler again to see if now everything is fine. It is still having an issue, but this time it's only a warning, which is not that bad, but we want to have code that will be read by other people, and by convention, constants are supposed to be all uppercase, and this is why it suggests us in the help to change the variable name from lowercase blah to uppercase. We are being nice programmers, so we'll also do that. Let's jump over to the code, go to line 20, and do this, save, jump back, run the compiler. It does not complain. We can run the binary. We will see our output. Now here we get to introduce the new cool macro. So the first lines are fairly obvious. It is printing out the value of x, then again x, this delta being an I. Below we now do our declaration, we do the output, and something is actually printed. And now we get to our debug macro. The print line is just printing to standard out, and you have to actually give the format string and the arguments. The debug macro works differently. It takes the argument, prints out what the argument was, and also where in the code it is located. So on the left you can see now that it tells us it's in variables.rs. In line 18, the variable y was passed as an argument, and it has the value 5. Same is happening in line 22. And this is very good for people that like printf debugging, because you can put this anywhere in the code, even within a computation, because as another property of this macro, it returns the value that you pass in. So if you were to put this here in the code, this would still compute fine, but you will also get your debug output. This means you do not have to write or add extra lines for your printf debugging. You can actually just inject it into your code. Very practical. Next, we will look at the scope of variables. For this, we have to jump back into our Python code, edit my prepared scope example. I also have that in Rust. This time the code's examples are not the same because this is not working equally in both languages. Let's directly play with this source code. And this means we jump into the shell for Python and run the scope code. We can see the output. It's a bit confusing, but let's bear with me. Since we are calling the subfunction here, it is putting out the local variable below. We change the global value to be 9, so we put it out here, and local becomes 1. The usage of our built-in scope here, for example, the integer function, is not printed. Now let's play with the code, as we said. If I jump over and go to line 12 and do this, then we will run into a funny issue with the scope in Python, because now it will not let us do that. So now the Python code understands that we have already a local variable in our subfunction, and therefore up here this cannot work because we have not yet assigned it, and therefore we get this unbound local error. So there is scope handling that can be finicky in Python as well. Let's fix this back to being a comment, and we change this line to see if we can actually print the enclosed variable coming from the sub function. And we will see that scope does not let us do that either, this time with a different error. It is telling us that this enclosed variable is not defined. Let's run this in the compiler, and it does not work because the short-lived binding variable doesn't exist in this scope. Why is that? Well, the short-lived binding is inside this block. If you have the curly braces beginning and ending without any further identifier, like if, for example, or a function definition, it still denotes a code block. This can be very practical in Rust because a code block is also a scope block. At the end of a scope, it will clean up memory for you. And therefore, you can limit your resource usage with this, for example. Now our resource goes away that we initialize here, and is no longer alive because this print line statement is after the end of the block. Now, in order to fix that, we simply make this a comment as well. And now Rust does no longer complain about our scope code, and we can see that all of those other bindings work fine. The further explanation of the scope in Rust is coming from those comments fairly easily. So here we have our long-lived binding that we actually bind here again, but it shadows the outer one from this is in the main function and this is in our code block. So if we print this here, we actually get our 5 and not the 1 that we have here. But since the end of the block also cleans up this binding, we no longer know about the 5, and here we can actually show that this is the value 1, and we can shadow it again, this time within the main function with the single character A, similar as I've showed already in the very first variable example. Next we will look at the numbers. Let's see how that goes. For this, we will open the numbers example on the left and the numbers example on the right. Numbers. In Python, you don't really have to declare the type. It will be inferred for you automatically. So for this -1000, Python will know, okay, this will be a signed integer. And if you put a really large integer, it will just grow it to 64-bit or even 128, I think. On Rust, you are required to give a variable a type. So in this case, it's an I32. This means it's a signed integer with 32 bits, and we give it the value minus 1000. If you don't want to use the colon and the type description, you can also just use the number, so minus 1000, and then right after attached it I32, and the compiler will understand that you are meaning that. Now the unsigned ones would start with the U, so you have unsigned integer with U64, now meets 64 bits. Here we assign the value 100. Equivalent below you can see 100U64 as the declaration without the colon notation. If you're writing really large numbers in both languages, so in Python since version 3.6 and for a long time already in Rust as well, you can use underscores. So if you have like here a 9-digit number, if it is just in one go, it's hard to read, but if you put it in 3 blocks as thousands would denote, you can use that separator with the underscore. This underscore is also practical for your type declaration. So below here in the float example, I actually use the underscore before the F32 because as you can see up here, if I just put the I here, you can easily miss that this is actually part of the type declaration and not part of the number. If you use the underscore before that, it becomes even more readable. And again, the same in float can be done with the colon F32 is now a 32-bit F for float, and you can give this a value. In Python, this is very similar. You already know that, so you get to do this that way. Complex numbers are part of the Python standard library, so you can just use complex like this, and it will work fine. They are not part of Rust standard library, as I denoted here. You would have to use a crate. For example, the num crate has complex numbers, and there would be one that is initialized by integers. And if you do it this way, you would have complex numbers doing with float. Now, binary literals in both languages can be written in a very similar way. So you start with 0b, as you can see here at the beginning, and the same is happening in Rust. And after that, you can write the ones and zeros for your binary notation of the, in this case, 8-bit number, unsigned integer number. And with the underscore, again, it will help you, so you can divide your byte into 2 nibbles, and you will have your 4 bits, and it will be easier to get where you are within your binary code. If you were to now combine those two, this will be 255, and this works in both languages. Hexadecimal numbers are also denoted in the same way. So 0x starts the hex notation, and then you can use AF, for example. And the same again with the underscores if you have really long ones. And in this case, it's combining like all the features that we've seen already. So you have 0x for the hexadecimal. We use the underscore to make 2 blocks of 2 times 8-bit. This then makes 32 bits, so it's an unsigned 32-bit integer, fairly easy to read actually. Booleans, as you know in Python, you have to use the capital T to denote the true, and capital F in the writing false for false value. In Rust, this is all lowercase, so true is a keyword and so is false. Not strictly a number, I know, but most people use that as zeros and ones. Continuing, we will look at typecasting. Now, let's open the example for that in Rust and in Python. Python is much shorter because there's not too much stuff that needs to be looked at, actually. So let's go check out our Rust code in comparison. Now at the beginning, this is pretty straightforward. We have our f variable up here, and it is an f32 with the value 1.23. And below, we just interpret this as a U8, an unsigned 8-bit integer. If you use that, you will lose precision, of course, and but it will be a fast operation. In Python, a similar thing, if you want, would be if you just use the int built in to make this an integer. Below we are printing the values. Below we have another example. Now if it does not fit, for example, if we have 16-bit unsigned integer with the value 128, if you now were to put this into a signed integer with only 8 bits, this would be too big, as a signed integer only goes to 127, as you know. The effect we will see when we run the program. And if you put it into an unsigned 8-bit, it will work fine because 128 fits actually inside. If it is too big in general, like a 1000 would be too big for the U8, you will also get an interesting result. And then Python automatically adapts the size of the integers, as we said, but this is not true for Rust because you declare the type at compile time, and therefore it is known to the compiler and used strictly in that form. So we have declared this unchecked function that we have here that gets an integer, a signed integer, 32 bits as 2 arguments, and also has this as an output. And we use this special wrapping multiplication function to do the multiplication. And below we do the same actually, but this is called checked. And the comment also gives away what will happen if we overflow the integer 32 bits. This will panic in debug builds. So these are two large numbers. If we multiply them, then we will overflow the 32. And this is a sign of a potential bug maybe. If you know your code needs to wrap and behave like old standard C code would behave, then you will have to use this wrapping multiplication function. And to compare float numbers is a very interesting problem. For this, we will look at later. Let's first run the Rust code just for fun. Right after the Python code, actually. So we can run the Python cast example, and it will show us that the float are not equal and equal because there's too many zeros. It is basically interpreted as 1.32, and therefore they are considered equal. This is the fun with floating numbers, floating precision numbers, that we will have soon in Rust as well. No, wrong. Back to Rust, we compile that cast example. We run the cast example, and it dies on us as predicted. Here we get the panic to multiply with overflow. So if you want to see a full backtrace, we can use this variable, and this is helping us because there could be code that is not supposed to overflow, but in some conditions it does, and it would be unnoticed. In other programming languages, in the debug build of Rust, it will not be unnoticed. It will actually panic and therefore stop your execution of your program. If we want to get rid of this, we can actually just compile this optimized. And now the result of our multiplication in both cases is the same because it behaves the same. The checking of an overflow happening is of course taking a lot of extra instructions on the CPU, and of course disables the compiler for doing lots of other important optimizations. Therefore, in optimized build, this is not a check that will happen. However, if you wanna show in your code that it is wanted behavior that your multiplication can wrap and it's fine, say you're computing a checksum, this is often done in all the code, then you should use this wrapping multiplication and not just the star and just run optimized builds to get rid of the panic, because then other programmers will know, oh, it's fine that this wraps and there's no issue. Now that we have the optimized build, we run further down the code into our float EQ example. Now let's check what this actually does. We will have to scroll down a bit in the code. So here we have the example. This is our function. It's very simple and not As you can see here, it is a hack. It's not very compatible to lots of stuff. However, if you want to check the equality of two floats, it is the smartest to do difference between them and check if they are below a certain threshold value. And this threshold can be different to your application, very small or actually fairly big. By default, Rust gives you this F32 in this case, this epsilon value. You can also look this up for F64s and other float types. And our code up here does the debug output of the comparison in both directions. So this shows that this 8 minus b absolute value is actually behaving correctly, because in both cases we can see here that these are not equal, because this is a sufficiently large difference, no? Just adding a third digit after the comma. And below, we can see that this is actually true in our thing. So apparently the F32 epsilon is smaller than these lots of zeros with the 1 coming in. And below, we can also see that the normal equal comparison operator is telling us that this is true. So they are considered equal even by the compiler. However, if you use assert equal with the same numbers, it actually errors out and tell you that the assertion failed, and shows you that these two numbers are not the same. So what I'm trying to show with this is that float treatment, especially in a compiled language, is very hard and should be done correctly. There's a fairly good website that explains and has good examples of how to deal with this problem. It's called Floating Point Guide, a bit funny spelled with .de at the end. I just realized I forgot to talk about the typecasting and the effects of it. Let's go back to the code up there to show the comparison. Now in the output we have the I being 1 and the float being the 1, 2, 3. So F32 gets to unsigned int and just becomes the 1. So we forgot about everything after the comma. And here the problem with the unsigned 16 bits that get into a signed 8-bit is funny, because we start with a positive 128, but the signed 8-bit gets the first bit set, meaning it's negative. Therefore, we get a minus 128 out of this with the typecast. So that's potentially dangerous if unwanted. If we do it to an unsigned 8-bit byte, we end up with the same number, so no issue. Here's the too big example. We have the value 1000 going into 8 bits. So now we have 232. This is explained by the least significant 8 bits becoming the value of this new byte. And in the case of 1000, this ends up being 232. So be careful with your typecasting. It might backfire on you. Thanks for watching. Coming up next on the From Python to Rust series will be ecosystem and tooling in Python and Rust, to get a feel for how the whole ecosystem works for you.